he thought the oil pressure gauge was broken when he first took it around Queensland Raceway because it didn't move.
Okay.
So he had 80 or 90 pounds of oil pressure and the gauge didn't vary. It stayed locked on 90 pounds the whole lap, and he thought it was broken, and he came back and checked it. And it's just because the block isn't moving, so that the clearances between the bearings and the crankshaft are remaining consistent, and so he's not getting variations in oil pressure.
Welcome to the HPA Tuned In podcast. I'm Andre, your host, and in this episode, we've got Darren from Billet Race Engineering in Australia joining us. Billet Race Engineering, well known for their range of billet aluminium engine blocks, and you're going to find these blocks in some of the fastest and most powerful drag cars and circuit cars around the world. Anytime we post anything about billet blocks, we inevitably get a handful of people complain that when we replace the factory cast iron or cast alloy block with a billet version, well, obviously at that point it's no longer a 2JZ, RB26 or 4G63 or whatever it may be. And while yes, I do understand this argument, I'm not here to say whether that's right or wrong. What I do know is that when you're starting to push the limits in terms of horsepower, at some point the factory engine block will become a limitation. Also, with some of these blocks now going out of production, it's becoming increasingly difficult and also increasingly expensive to source replacement factory blocks, which starts to make the billet version look like an attractive and cost-effective solution. In this interview, we dive into Darren's background, how he actually got his start in the automotive industry, which is relatively unique, how he ended up purchasing an engine machining and engine building operation, how he moved into head porting and purchased one of the first 5-axis CNC head porting machines in Australia, and then how he transitioned that into building billet engine blocks. We dive into some of the common limitations and failure points of factory cast iron or cast alloy blocks, and we talk about how going billet can solve those problems. Also, how a billet block can be more serviceable than a factory cast block. In particular, in some instances, it can be possible to repair a billet block that's, for example, had a conrod go out through the side of it. Now, before we jump into our interview with Darren, just for those who are maybe new to the podcast, High Performance Academy is an online training school. We specialise in teaching people how to build quality, reliable street and race engines. We also cover topics such as engine tuning, building wiring harnesses. We also cover race driver education, race car setup, and even some fabrication topics. You can find all of our courses at hpacademy.com/courses, but relevant to our conversation with Darren today is our engine building fundamentals course and our practical engine building course. Our fundamentals course, as its name implies, covers the fundamentals of engine building. You'll learn all about the assembly process of the engine, all of the components that go into the engine. You'll learn about the common machining operations that we will require to take a factory road-going engine and basically repurpose that for a competition use. This will allow you to speak the same language as your engine machinist. You'll also learn about the clearances inside the engine, the tolerances that go along with those clearances, and how some of these clearances may need to be adjusted when you take an engine that perhaps was designed to produce 300 horsepower at 7,000 RPM, and you want that engine to produce 600, 900, maybe 1,200 horsepower and run to 10,000 RPM. You'll learn about the selection of the components that go along with the internal assembly of that engine as well. Now, moving on to our practical engine building course. This builds on the knowledge taught in our fundamentals course. This time, as its name implies, we jump into the practical assembly process. And I know that this can seem a little bit daunting, particularly when you get your freshly machined components back from the machinist. What do you do first, and what process or what steps should you take? What order should you proceed in? Well, what we've done within this course is broken the entire engine building process down into the HPA 10-step process. By doing this, each of the individual steps is quick and easy to complete. And in no time, you've got to the end, you've got a properly assembled engine. You're going to be confident that the assembly has been done correctly, that every clearance inside the engine is exactly what it should be. And this is going to give you the confidence that when it comes to start it for the first time, it's going to produce great power, great torque, and most importantly, deliver excellent reliability. Now, that 10-step process is generic, which means that you can apply it regardless whether you're building a inline 4-cylinder, an LS V8, V12, or essentially anything in between. We then dive into our library of worked examples, which is where you can watch that 10-step process being applied from start to finish on a real engine building job. And this will give you a broad range of experience on different engine platforms. Now, if you are interested in either of those courses, we will put a link to both of them in the show notes. And as a podcast listener, you get to use the coupon code podcast75. That will get you $75 off the purchase of your very first HPA course. All right, with our introduction out of the way, let's jump into our interview with Darren now. All right, welcome to the podcast, Darren. Thanks for joining us today. And let's just get started with a little bit of your background and how you sort of got to the point of operating Billet Race Engineering.
Okay, well, when I left school, I did an apprenticeship as a fitter and turner. And the timing of that was impeccable because when I came to the end of my time of that apprenticeship, which was at the Australian Railways, was right in the middle of the recession in the early 90s, and they laid all of us off. And so then I did some welding for a while, and then I actually went to university and did a business degree majoring in real estate valuation and economics, and my hobby was drag racing. And
that's an eclectic set of skills there. Okay, let's carry on.
So that was my hobby, and the idea was I was going to get into real estate and work in the corporate environment and make a lot of money and use that money to go drag racing. And then after about 18 months, I hated going into the office. I just hated the whole environment. I'd been racing in the meantime and associated with different people. And I convinced a local engine builder who had about 30 years experience to sell me his business and work for me for 2 years to teach me everything he knew. At the time, I know a lot of people thought I was crazy for what I paid him and all the rest, even though they didn't really know, but they didn't understand that I wasn't buying the business. I was buying what was in his head. So I continued with that, and that was under my business name was Adelaide Engine Developments. And so we did sprint car stuff, and his business was in the back shed, and I moved it into a building, like industrial building, and we put a dyno in, put an engine dyno in, did some other things like just to bring it up, bring the level up. And then sort of he left after 2 years, after his contract was up. And I was looking at the business, and I just thought that there was you could make a living out of it, but there wasn't really a future in it because it's just a structure of just being an engine builder. It's so competitive, and there's so many people, and there's people operating out of their homes, and so the overheads are lower, and it just makes things difficult. So then I was looking at what was happening in America, and they were always at least 10 years ahead of us, probably at that point even more. And I could see it was going with CNC porting where it was going. So I contacted a friend of mine, Marcus Jobby, who had worked out of Peter Schaefer's workshop porting cylinder heads since he left school, and he was very good at cylinder head porting and a lot of national record stuff and that. And I asked him if he wanted to go into a partnership with me to put a CNC porting system in. So at that time, there was only one CNC porting company in Australia, in Western Australia. And then actually just before we did it, Performance Wholesale put the same system that we were purchasing in, and about a month before. but they had some issues with staff and they hadn't got it going yet. And so we put the system in. We flew an American in. We put the system in. He did the training. And so we were actually the second company in the country to ever CNC port heads. And so then we were just moving forward that way with the system. But like we went out on a limb to do that, and it didn't work out the way we wanted. So there wasn't enough work. And that's a combination of the market here and also us not really knowing what we're doing in terms of marketing.
All right, let's just stop there for a moment because you've covered a bunch of ground. So let's just go back and cover off a few of the aspects here. So starting out, qualified, trained fitter and turner, then moving into purchasing this engine building business. And generally, I mean, I understand, obviously, you mentioned you've taken on the owner there on a contract for 2 years to train you. So, typically, and this is something I sort of see across the world, typically with engine machinists, engine reconditioning shops, there's quite a disconnect between those who have gone through the qualification process to become an engine machinist, but they kind of spend 99.99% of their time machining and building garden variety, low-powered, naturally aspirated engines, and there's quite a disconnect between that style of machine work and engine assembly and those who specialise in performance engines, where generally we like to work to slightly tighter tolerances, and the end result, the power, the RPM range that the engine is going to be working at is significantly different. Can you tell us about your experience sort of building up that knowledge and how you sort of develop that learning from the owner?
Yeah, well, look, what a lot of your listeners may not realise is that motor mechanic, engine builder and tuner are three completely different things. And what happens is in the industry you get a lot of overlap where you get motor mechanics that like to think of themselves as engine builders, and you get tuners that also like to think of themselves as engine builders. And usually the engine builders just stick to engine building. But even with an engine builder that only builds, or the majority of their work is standard reconditioning, there's still a good engine builder, because just the discipline of it in terms of what to look for and how you approach things so that you don't make a mistake.
The fundamentals remain the same.
That's right. And I mean, of course, you've got the wrecking yard type guys that are just going to slap stuff together and, 9 times out of 10, they get away with it. But in terms of racing engines, because they're going to be put through a lot tougher or put through their paces a lot more than a standard engine is, if something's slightly wrong, that can turn into a big problem. So it's more so like in terms of my training in those 2 years, we don't do standard engines. I'd never done standard reconditioning engines. We just don't see it. So it's all racing. So the whole thing with an engine builder is there is no real training for it outside. I mean, there's technical colleges in the US, but even so, it takes experience to understand what you're doing and do it in a way to minimize mistakes.
Sure. I think it's valid to sort of mention there the training, and I mean really this goes across everything, regardless whether you want to learn how to build engines or play guitar. I mean, you need to understand the fundamental skills, how the engine assembly and machining process works, and then it's the old story of 10,000 hours of practical experiences is what they generally say gives you expert status. So there's nothing can change, or nothing can replace the actual hands-on experience that you do need to put in that time to actually become competent, see all of the weird little problems that you see as you go through building hundreds of different engines, and sort of, again, just nothing that can replace that. Now, another aspect you mentioned there is at the time you purchased that business, you said that Australia was maybe 10 or maybe 15 years behind the US in terms of particularly sprint cars. It's quite a competitive class of racing. Specifically, what was it that you were 10 years behind in?
It's in the technology. So what you could see is they started out trying to CNC port heads. So I'm talking specifically about cylinder heads.
Okay.
So that business we named it Bullet Cylinder Heads, which was a mistake because at the time we thought we were going to do a cylinder head business, even though we were engine builders as well. And then, of course, from a marketing perspective, everyone thinks we only do cylinder heads. And so that reduced our market reach because people didn't bring engines to us to build. But what I mean by 15 to 20 years behind is in the technology. So they started messing around with that back in the early 90s. And by the time you got to 2003, when we started Bullet Cylinder Heads, there wasn't a lot of hand porting going on. I mean, in the lower echelons there still was, but in the upper echelons of racing, where they were really making the power, that's all CNC ported stuff. And because what it does is it allows you to develop port shapes by a factor of 10, because the machine does the work of 10 men, and so you can spend. Instead of spending 40 or 50 hours trying to race port a set of cast iron heads or even aluminium heads, you can just concentrate and spend even 10 or 15 hours on one port and get it, 5% better than what you would have with doing it the other way, because you can put that time into it and then you can just replicate it on the machine.
I guess the other aspect with that is because you're relying on a machine rather than hand porting, you can get that consistency across every port on the cylinder head that is going to be much more difficult to replicate accurately by hand.
Yeah, it's impossible by hand, but the other thing is that, that has an effect on power as well, because, it evens everything up. But it's more so that, and this is what comes from my economics training, even though the majority of it is rubbish, but it teaches you that if I'm looking at from a business perspective, I'm looking at then how can I differentiate my business from the other ones in the industry, and how do I make it more difficult for someone else to do what I'm doing and become a competitor? And by investing in the equipment and using technology that not everyone can do, right? Because, you could put an engine together, but you might not have the skills to run the computers and get into the CAD CAM, because that's a whole nother level. So that's
not to mention the financial outlay required to purchase the CNC equipment in the first place. That's going to be a hurdle for a lot of businesses that they just can't overcome, correct?
That's right. And so, you take the chance that something's going to come of it. But then once you get there, then it's like, well, now someone says, oh, I'm going to start making billet blocks or do this or do that. It's like, okay, well, get $2 million out and buy all the equipment and put in the thousands and thousands of hours trying to program and figure out how to make it in an efficient manner, and let's go.
Yeah, that really does put it into some perspective. I don't want to dwell. Obviously, we're here to talk primarily about billet blocks, but this is interesting to me. So I'll come back to one aspect of the engine machining, assembly, and cylinder head porting side of things. You did say that you put in a dyno. How critical was that in terms of you developing the CNC head porting sort of programs for a given engine? Are you sort of going through a process of hand porting, validating on the dyno, iterative modifications from there before you finally settle on a particular program for a given cylinder head, or is that being developed just through the experience of the porter that you said that you went into partnership with there? Or alternatively, you're also using something like a flow bench for the head to help develop that. And this is an area of the engine that I definitely don't focus on myself. Porting is not something I do, but there's so much to it, as I understand it, sort of where there is that kind of almost merge of science and art, and it's a case of bigger definitely isn't always better as well.
Yeah, so the real the honest answer on the dyno is that the biggest advantage of putting a dyno in, and I'm talking about an engine dyno, is that at the time there wasn't very many in Adelaide, and what it does is the other engine builders bring engines to you to dyno them. And like all engine building, you learn more from your mistakes than you do from your successes. And so what you do is you get to see what other people are doing, and you get to see the mistakes that they make. And you get to see, because, we always say there's more tears and cheers come off the dyno, because they come to the dyno with their high hopes, and they usually get shattered. And so what you see more so than not is like 90% of the time you see what doesn't work, and or what not to do. So
fast tracking your own sort of development based on the failings of others. Well, maybe not the failings, but just the misses.
Yeah. So what we see is it complemented my idea of buying that business for the knowledge, was then putting the dyno in, which went in within months, enabled me to just learn a whole heap more. So basically it enabled me to get 20 years experience in the space of 2 years.
Sure.
And so in terms of developing cylinder heads, that just comes back to Marcus's ability of, when you work, he worked in a head porting business. It wasn't even an engine building business. So it's cylinder heads, racing cylinder heads, day in, day out for a decade. And, you just can't help but learn a lot. So basically at the start, we were just working off of his experience. And then later on, we actually did the advanced induction course with Darren Morgan out of Rare and Morrison, and that brought more science into it. So that brought things up to another level, because there was different things that we were looking at to develop ports. But a lot of it Marcus was already doing. He just didn't know that's what he was doing. He's just doing it from experience. And then when you can put the science behind it and you start calculating the numbers, then you can see that, okay, that's why that works better.
All right, so let's sort of talk about the move towards the billet engine blocks. Am I right here in assuming that this sort of stemmed from the fact that maybe the cylinder head porting didn't quite take off like you'd expected? You've sort of got an expensive CNC machine and some knowledge around running it, and you're looking for other things to do with it to make it sort of earn its keep?
Yeah, that's exactly what happened. So what we did was we weren't getting anywhere. We just didn't have the volume of cylinder heads, so we just sort of bumped around on the bottom for a few years, and then we started making alternator brackets. And so we made alternator brackets and timing covers for Holden V8s. And the reason we made them is because no one made them. And it was relatively simple. We didn't need a lot of tooling. So we started making that, and then we moved into Cleveland's and Chryslers and different things. And then in 2010, we'd built some Japanese stuff. So I built some customers that had run V8s. There was some overlap there, and we built we had a guy bought an OS Geekin out of Japan, and it was a short motor, and we wouldn't put our name to it just without pulling it apart and checking it. And luckily we did, because it was terrible. In fact,
you're talking here the OS Geekin 3-litre RB, is that correct, with the high deck block? Yeah, okay.
No. They got a plate in there to raise the deck. But I mean, it was that bad that one of the pistons was an interference fit in the ball. Right. Only by
so this is straight out of Japan. No one's actually touched it. Brand new engine. Brand
new engine. And I remember in the industry, the local industry here, they said we were crazy for taking it apart because we'd screw it up. But when we took it apart, I mean, there was just issues after issues. So anyway, we fixed that engine up and it went together and he did quite well with it. And then I did some SRs. And so because I was in that sort of moving into doing a little bit of that, I did notice that the people operating that industry really had no experience. And there was a lot of rubbish coming out in the import industry, and all the experienced guys that had been doing V8s weren't really working on them. And so I thought this might be an opportunity to shift the focus of the business into an area where our competitors aren't really up to scratch. And so,
what sort of year are we talking here, Darren, just to give some context around
back then, that was, I mean, the OS was back in 2001. But then, you know, then some bits and pieces with some SRs in between. And we were CNC porting 4-valve heads. And I just looked at it and I thought, you know, like they're putting these turbos on these engines and they're exploding them and they're breaking the blocks. And I could see, obviously, again, in America, they had billet blocks for V8s and they had aftermarket blocks of Brad Andersons and Keith Blacks and Alan Johnsons and all that. And I thought, no one makes them for the 4 cylinders and 6 cylinders, the import guys. And so I just thought, well, you know, that's what we did with the alternator brackets. We make something that no one makes. They're low volume, but it's all right for us. And so I thought, let's make an SR20 for drag racing. But we had to have water in it, was the thing. And so we made the first SR20 in 2010, and it went into Ben Bray's car. And Ben Bray set a world record with that car, with that engine in it. And it was very agricultural and very basic, but it worked. But back then, though, the exchange rate was quite high, and so that the exports were hard because we were expensive. So then it didn't really take off until Murray Coote used the SR20 in Time Attack. And then people saw that the water cooling, because no one believed the water cooling would work in the billet block. They just...
Yeah, I mean, conventionally, if we look at the billet blocks that you mentioned before from the likes of Alan Johnson, Keith Black, these are dedicated drag blocks. There's just no water jacket in them. There's no requirement, of course, the engine runs for a few seconds down the drag strip, gets shut off and gets towed back. So particularly when you combine running on methanol fuel, the cooling and properties of that, coolant is just unnecessary, correct?
Yeah, that's right. They can get away with it, and it makes the design and manufacture of the product much easier when you don't have to deal with the water. And so we did the one for Ben, and then he was friends with Colin Wilshire, and so we did a Mitsubishi for Colin. And again, that wasn't something that we could sell. It was sort of a hybrid type thing, and it was very chunky, you know, very thick and basic, just enough to get the job done. And then, you know, of course, Colin started going fast with that as well. And so, yeah, as I said, once Murray used it in Time Attack, and at the same time as he used it, he came second that year, and then the exchange rate started to move in our favour. And then all of a sudden the phone started ringing and people asking about doing it. And then around about that time, I had a friend of mine that was helping us after hours, who was an experienced software engineer, applications engineer for SolidWorks and programmer. He came to work for me, and that's when our designs started to change to become more intricate. And then we bought another machine, and that was more dedicated to making blocks, because basically we were using the CNC porting machine to make the blocks, but it wasn't ideal.
All right, again, bunch of information I want to come back and sort of dive into a little bit here. So around this time, sort of essentially what you've said, you were basically at the forefront of producing import-style billet blocks. No one else at that time's doing it, correct?
Yes, we were the first. And then
Okay.
Mazworks made an SR20 not long after we'd released ours.
All right. So let's talk about that SR20, because I think it's probably a really good case study in, you know, the weaknesses or limitations of a factory block versus the advantages that the billet block gives us. So first of all, unlike earlier engine blocks, the SR20 went to a cast alloy, which is pretty much the norm these days. So first of all, one of the downsides there compared to a factory cast iron block is we lose a little bit of strength just given the material. Obviously, there's an advantage there in terms of weight. Then we've got problems which we've experienced ourselves with the factory caps, which can crack around about the 400 to 600 horsepower, depending how lucky or unlucky you are. You've got the strength of the sleeves that are inserted into that cast alloy block to actually give the ring something to run on, the integrity of those, reliability under high cylinder pressure, and of course we've also got problems with head gasket integrity once you start getting into the very high boost levels. So Can you talk to us about how the billet block addresses those individual aspects?
Yeah, so what we're doing is when we first design those things, I'm looking at what were the aftermarket blocks in the V8 realm doing. So, of course, I'd seen a lot of those blocks with my experience over the years, and it's not rocket science, but it's like you increase thicknesses where you can, you add additional bolts, like for the main caps, and, you're going to increase your deck thickness, you're going to increase the cylinder wall thickness, and basically design the block in a way that it will still fit within the factory parameters by and large, but it makes it more rigid. And so the reason that blocks fail, aside from like a conrod failing and putting a window in a block, but the reason that the block is the failure point is because it's moving. And when it moves, it moves to a point beyond the yield capacity of the material it's made for. And as soon as you go beyond yield, you're going to develop a crack. So the idea is to make something that's rigid in the areas where it needs to be, and then also in a way that comes down to how you prepare it when you put it together, is that you want to radius areas and get rid of sharp edges, which is just standard race engine building stuff, because that's where a crack's going to develop, because that's the tightest point. Like when you come to a point, then it doesn't take a lot of movement for a crack to start from there, because it's not like it's moving over a distance of a meter, where it would have to move a whole lot before it cracks. If it's you're
getting that concentration of stresses at sharp edges, essentially.
Yeah, and so that's where the crack starts, and once it starts, it's not going to stop.
Of course. Okay, so you mentioned the thickness of the deck surface. So for non-engine builders, we're talking here about the top surface of the block where the head bolts on. And I mean, I think probably those who haven't been involved in the likes of drag racing or the top echelons of World Time Attack probably wouldn't experience the frustrations of head gasket sealing issues. But it is a very real problem when the cylinder pressures start climbing. And I think we've talked about this before in some YouTube videos, Darren, but just to reiterate there, one of the common solutions, people think that just going to a larger diameter head stud with a lot more clamping forces is going to be the solution. And of course, it isn't always going to be a solution. We do get essentially a situation where the thickness of the deck surface on a factory cast iron block or cast alloy block is insufficient. There's not enough integrity there, and it can actually flex along with the head, correct?
Yeah, so while putting a larger head stud or a stud with different material with a higher clamping force will improve things, it's still in the midpoint between the two studs on the cylinder. is where you'll usually see a head gasket fail. Like, it never fails right next to the head stud, because that's where your clamping force is at its maximum. And that's just because the material isn't rigid enough, the clamping force at the midpoint is going to be lower than what it is right next to the stud. And so by increasing the thickness there and the way the shape of the material underneath the deck and around the cylinder, then what you're doing is just allowing for less flex. That's all you're doing. And so that just means that there's more clamping force on the gasket all the way around. And then you'll still get to a point where the limitation of the cylinder head is what causes the gasket to fail, because the cylinder head is suffering from the same problem as the factory blocks, just to a lesser extent. So that was the main thing. And again, that's just, when you look at a dart block, for instance, in a V8, that's one of their advertising points, is it's got a 3/4 inch deck.
So you're not really reinventing the wheel here. You're taking existing technology that's been developed and proven over the years with these US aftermarket block manufacturers and just incorporating it into your own design for import engines, correct?
Yeah, and I mean, I think the big difference with ours is that our water-cooled blocks are still a Siamese bore and dry sleeve, which there's a lot of options out there to do it a different way, but it doesn't give you the rigidity and the integrity in the block, because the block acts as like a beam as well, where one of the comments that Murray made when he got the first engine was he thought the oil pressure gauge was broken when he first took it around Queensland Raceway, because it didn't move. So he had like 80 or 90 pounds of oil pressure, and the gauge didn't vary. It stayed locked on 90 pounds the whole lap, and he thought it was broken, and he came back and checked it. And it's just because the block isn't moving, so the clearances between the bearings and the crankshaft are remaining consistent, and so he's not getting variations in oil pressure.
That's a good next topic to discuss, is that integrity of the bottom end in terms of how the crankshaft is retained. And you've already mentioned that one of the changes you made on the SR20, and I think you've carried this across to all of your block designs, is moving from a conventional 2-bolt design where each of the main bearing caps is individual and is bolted into the block with just 2 bolts. And from what I've seen with the SR20, if I'm correct here, essentially you've designed a full lower girdle, which basically is the lower half through the crankshaft centerline of the block, and that's doweled and also bolted into the block with 4 bolts at each of the main bearing caps. Is that correct? Does my memory serve correct there?
Yeah, usually we only run 2 on each end. The new Barra block has 4 on each end, but we usually run 2 on each end because the end bearings only have to deal with one cylinder, whereas the middle bearings have to deal with a cylinder on either side of them. So you like to have more clamping force there. But yeah, I mean, we did that. You see that in some factory engines like the VR38. And also the K-Series Honda, they do that. But we did it because to give us the integrity, but also it does make the manufacturing easier, or it makes it a different process, because you don't have to start with as thick a piece of aluminium, because you're splitting it at the crank center line instead of having the sides of the block come down and then a cap that sort of sits up inside the pan rail. So that makes the piece of material that you have to start with 3 inches shorter to make the block.
So it just improves the economics of the process.
Well, it does. I mean, you have to do extra work because you've got to make a cradle as well, but also you don't have to use long tooling. So you can use shorter tooling to get into the crankcase and machine it out, which means you can do it faster.
Sure.
So there's various reasons for doing it, but the way that system works is, it makes it very rigid at the bottom, and, people just don't have bearing issues.
Yeah, so I want to dive into that because I think this is something that those who are new to engine building, tend to overlook. It's very easy when you've got a crankshaft and an engine block sitting on the workbench to look at those components. Obviously, they're very rigid there under those conditions, and you sort of think, well, fine. I mean, that's what we're dealing with. Nothing's going to move around. But the reality, of course, is that when we're making 1,500, 2,000 plus horsepower, 10.5, 11,000 RPM or whatever it may be, all of those components are under huge amounts of stress and do tend to flex. The crankshaft's going to flex, and that can result in bearing contact or bearing issues, getting rid of that, removing that oil film that protects the bearing and journal surface. And also the other part with a factory block, and I see this time and time again when you start ramping up the power level, is if you pull one of those main caps off, or a cradle in the likes of maybe the 4G63, and you look at the mating surface between the two components, and you can see signs of fretting, which is microscopic amounts of movement between the two components. And the only way we can get that is that the cap or the cradle is physically being sort of lifted off its mating surface under high load and allowing that relative movement that results in the fretting. But the upshot of that as well is we tend to, basically it creates a leak path for our oil pressure, so our oil pressure ends up reduced, which I'm guessing is what you were mentioning with the MCA hammerhead, where Murray noticed the oil pressure was much more solid. Is that sort of a fair summary of those aspects?
Yeah, I mean, that's what you see happening when you do see fretting. That is because in effect it is lifting, but it's got to do with the harmonics, and they're moving around. So the cap is moving around in the register of the block, and then of course the material picks up on each other, and then you end up with those fretting marks, as you mentioned. So, in terms of the bearing clearances, so that moves, if you get that to the extreme, which you're more likely to see in a conrod where the cap is coming away from the fork, the upper piece of the rod, then what it does is it actually hammers the bearing. So you get a hammering effect, and you'll see this with detonation. And so what it does is it hammers in the center of the bearing shell, and then it will actually pull the edges in at the parting line. And so when the edges pull in, they act as a scraper, and they'll scrape the oil off of the journal, and then you have no oil, and then it overheats and you run the bearing. So what a lot of people will look at that and they'll say, oh, we ran out of oil, but they didn't. What's happened is the bearing has pulled in, scraped the oil off, and caused the failure. And if you get to the point where it's a failure, it's hard, you can look at other areas of the engine to determine that's what caused it. But if you get it at the start and you pull the engine apart and you pull the rods out of there and the bearings fall out of the rod, well, then you can see that's what's happened. And it can happen on the main bearings too in extreme circumstances. And so sometimes that's what's happening. And then other times it's just because the clearances are changing so much that there's not enough oil pressure there, and people try and feed oil in different areas of the block so it doesn't have to travel as far to get to the end bearings and so on and so forth. But they're just band-aiding what's going on.
Yeah. A couple of aspects I'll just add there is whenever you suffer from an engine failure, the most important thing in my mind is a thorough analysis to work out what has been the root cause of that failure, because so many people overlook that, spend a bunch of money putting the engine back together and immediately have exactly the same failure occur because they obviously haven't fixed that root cause. That, however, and you sort of alluded to this just now, is often easier said than done when you've got a catastrophic failure, because there can be so much damage created in such a short period of time that often the sort of telltale signs that we would want to look for are kind of masked by the amount of damage that we see. So that can be problematic, but again, really important to focus on what has caused that failure. And another thing that's worth mentioning here is if you're monitoring oil pressure, and generally we sort of see a reasonably good correlation between engine RPM and our oil pressure. Usually, I mean, within reason, a good rule of thumb is the sort of 10 psi of oil pressure per 1,000 RPM, give or take. But if you're sort of seeing your oil pressure come up with the RPM, and then you sort of get to a high RPM, high boost situation, and you start seeing that oil pressure drop off, quite often that can actually indicate that you've got that sort of flex occurring or movement occurring in the main bearing caps, allowing the crankshaft to move, the bearing clearances to open up, and that oil to kind of leak out. So that's sort of something I would look for as a bit of a telltale sign if we're looking at data as well. Now, just moving on with the block design, one of the issues with an alloy block is, within reason, at least in the aftermarket, we're not going to be running the rings directly on the aluminium surface. Yes, in OE world, there are coatings that are applied, but for a performance application, we really want strength. So you can't run the rings directly on the alloy. So you're using an aftermarket sleeve, and you also mentioned dry versus wet sleeves. So can you talk to us about the differences between those, what those terms actually mean, and pros and cons, why you are using a dry sleeve?
Okay, so in the wet sleeve configuration, basically they machine the whole cylinder area of the block out, like we would refer to it like a shoebox, where they would machine it all out, and then you have no material between the cylinders. It's just one big hole that's specifically shaped to take the wet sleeves, and then as you put the wet sleeves in, they interlock, and then that allows the water to run all the way around the sleeves, and there you have your water jacket. But the problem with that is where your fastener goes is not where the sleeve is. It's not a part of the same material, and so and then you don't have the material joining between the bores, which is where we call a Siamese bore. So you still get some flex there, and so it is better than factory, but it's still, once you get right up there, it's not you'll start to get head gasket failures.
So you're sort of fixing one problem, but sort of kicking that problem a little bit further down the track in terms of power levels? Yeah,
I mean, it's a little bit like putting the bigger head stud in, like you get, it allows you to go a little bit further, but not all the way.
And just for a reference there, that would be common with the likes of the SR20, which obviously we're currently talking about, very common to do exactly that, have essentially the guts of the block machined out for the likes of maybe a Darren mid-sleeve style installation, correct?
Yeah, so the main ones they do it on, or the first ones I recall was on the LS engines, LS V8s, and then the VR38 is like that, even in the billet version. Even in our billet version, it's like that because it's just impossible to do it another way. And then on the SR20, I think there's a version there. So in some instances, you can't use that method because the bores are too close together and there's just no room. So that's your wet sleeve option. But the dry sleeve option is you've got the Siamese bore in the aluminium, and then you've got support on the sleeve all the way around, and also the fastener. There's no water in between the fastener bosses and the bore. So there's no room for movement there either. And so it just makes the whole thing a lot more rigid. But it just adds design complexities because you've got to machine the water jacket from the outside and then have a bolt-on cover to seal it. And then sometimes that can make it bulkier, so ancillaries won't fit, or ancillaries might have a mounting point right where the water plate goes, which then makes the water plate deal more complex to do. But that's where we put in the extra time to design them the way we do, because it's more about making something that's going to, fit in with what it's going to be used for, rather than making it look a certain way.
Okay, let's talk a little bit more about these water jackets. So conventionally, this is really an aspect of the way the factory block is cast. You've mentioned there that you've sort of come in from the side. And I mean, this is difficult to really explain without some photos. So, our followers here, our listeners, are probably just going to have to use their imagination a little bit. So basically, if we lay the block on its side, you're machining in through the side of the block down towards where the sleeve is going to go to provide an area for that water to flow. And then obviously you've got this open hole that you need to cover up, so then you're machining a separate cover that actually bolts in place. Now, in terms of the cooling efficiency or cooling capability of a wet sleeve versus a dry sleeve, I mean, just from a novice standpoint, it sounds like you would potentially have better cooling with a wet sleeve design because you're going to get that coolant directly onto that ductile iron sleeve closer to where the heat source actually is. Is that just not a problem? Does the dry sleeve work just as well in terms of cooling efficiency?
Yeah, look, a lot of people misconstrue the cooling in the block, and the cooling in the block is not critical. You need something there, but first of all, you have to separate it. So there's a certain percentage of the engine cooling is the cooling of the block, and then there's another percentage which is the cooling of the head. Now, the cooling of the head is much more important because that's where all the heat is. But also in the block itself, if you separate the block from the head, 80% of the cooling of the block occurs in the top inch of the bore. So this idea that you need a water jacket for the entire length of the bore and all this that's fine in a factory application where they don't want, recalls. But in racing and with the aluminium material, you don't need that level of cooling. And the other thing is that if you have a 14 or 13 or 1400 degree Fahrenheit combustion temperature, it's not like it's in an oven. It doesn't work that way. So in the combustion process, there's a boundary layer that occurs around the combustion, and that insulates the components from the combustion temperature. And this is, if you think about it, this is obvious because the pistons would melt. If the melting point of aluminium is much lower than 1300 degrees Fahrenheit, I think it's around 700. So how does the engine operate if the components are being exposed to that temperature? And it's because they're not. So what you find is of the combustion temperature, 70% of that goes out the exhaust pipe. And then you have to deal with what's left. And so when you get a detonation, which going back to your engine failure comments, 9 times out of 10, that's why the engine's failing, because it's detonating. But when you have a detonation, what happens is that breaks the boundary layer and then exposes the components to the heat. And that's why when you see the results of it, you see melted pistons or torched decks or cylinder heads and head gaskets. It's because they're actually getting exposed to that combustion temperature because the insulating barrier is gone. So the cooling has never been an issue. The only issue we've ever had with the cooling is getting people to accept that the cooling that we have in the block is enough, and that's what Murray did in Time Attack. But we only have issues in terms of having something extra to deal with in terms of oil cooling, because the blocks, the billet aluminium is much more efficient in transferring heat into the oil than the cast versions, and so you have to increase oil cooling capacity to keep the oil cool so it doesn't run away on temperature with you. Now, in a street application or drag, that's not an issue, but if you're going to do circuit racing, road racing, where you're going to put on 20 laps, you need to have something there.
Okay. Again, a bunch of information to unpack there. I'm really glad that you brought up that mention of detonation and the boundary layer, because I think that's something that a lot of people completely skip over, the fact that the full heat of combustion would simply melt the piston and the cylinder head. So yes, obviously, there is a mechanism there protecting it, and detonation, of course, breaks through that boundary layer. So that's why we see initially light pitting, and then obviously in full-blown detonation at high power levels, the side can get melted out of the piston in a very brief amount of time. Also, in terms of where that heat is located, I mean, when you think about the way the engine operates, it's pretty apparent that the majority of the heat's going to be in the cylinder head or high in the combustion chamber, and that's also another trick that a lot of people building the factory cast iron or cast alloy blocks, including myself, have gone through is partially filling the water jacket in the block with a block filling compound, essentially cement or grout as it's often referred to. And if you still need some cooling, the trick there was to partially fill the block, the water jacket, and I've had street applications where that's worked just fine, even though you've got maybe half or 2/3 of that water jacket filled. So that sort of sits in line with what you've said there. Of course, the other aspect with that grout filling process is if you're only partially filling the block, my concern has always been that the maximum cylinder pressure is really occurring up in that sort of same area where we see the maximum heat up in the top of the block. So we're probably not seeing the full advantage of partially grout filling the block in the first place, but probably a different conversation for a different day. In terms of your water jacket that you're using there, are you still feeding the water from the block up into the cylinder head through the head gasket, or is this done externally to keep a dry deck surface?
Oh, we have both options. So we have the factory option with an MLS gasket, and it feeds up through there as normal. So what we do there is we rate that at 300 horsepower per cylinder. So what we see is that, and this is from experience from clients, that we see them make in a 4-cylinder application, they seem to make 1,200 horsepower with an MLS gasket and not have an issue with the head gasket. And in the 6 cylinders, we've seen 1,800. I think I've had one client at 2,000 with an RB, but it just started to seep. But once they switched the engine off and let it cool down, the head gasket wasn't blowing. But I think they had a little bit of pressure get into the cooling system. So we sort of try and limit it at 300 per cylinder or less for that. Once you go above that level, then you would go to a dry deck where there's no holes in the deck of the block, and then you have two options there. First, well, you have to close the holes in the head as well, which you weld the holes in the head shut. And then you feed the water externally into the head, and that's where you have two options where you can feed the water into the block with the factory water pump, come out of the block and into the head externally with hoses, or you can split it at the bottom radiator hose and plumb water in and out of the block and in and out of the head separately. We don't see that. That would make people look at that and say, well, you're going to have colder water going into the head because it hasn't gone through the block first, so it might be better, and it may very well be, but we don't see overheating problems with either method. So,
and is this a setup that you would normally use in conjunction with the likes of an aluminium bronze sealing ring and then a copper gasket that's really in that instance only there to seal oil? Obviously you've got no water now going through it, so you've got your main oil feed, your high pressure feed up to the cylinder head, and of course the oil returns. Is that the sort of setup you'd use above that 300 horsepower per cylinder kind of line in the sand?
Yeah, that's what we do. We supply those style of gaskets, but there are people that are running those styles of gaskets with a water block, which then enables them to make even more power with a water, with an open deck block or feeding the water through the gasket. So we prefer not to do that because you still have a risk there of combustion pressure coming past the ring and getting into the coolant passages. And there's twofold to that, is that first of all, ends your day, and second of all, there's a safety issue because that's a track for water to come out and get on the track and under the tyres and cause an accident or something like that.
I think it's really easy to overlook how important that is. Many people would just consider the head gasket failure as being the main concern. But yeah, if you get some water under the tyres at maybe 150 mile an hour or above, that's generally going to put you straight into the wall, and the driver really doesn't have a chance to do much about it.
That's true. And I mean, that aspect comes back into making your choice on whether you're going to go to a billet block or not. And I've got examples. I have a B series guy in the United States who didn't want to spend the money going to the billet block, the extra money. He was presented with a decision or whatever was going on at some point, and then I think it was within the following meeting or the one after, he broke the block, oiled down underneath the tyres and hit the wall. So luckily he didn't get injured, but what it showed was that his decision to save a few $1,000s ended up costing him tens of thousands of dollars. And so that's when people are looking at investing in the billet blocks, they don't have to only consider the money that they're going to spend there and then on making that decision. It can save you a lot of money in the long run because of those issues there.
Yeah, I mean, obviously no one ever wants to see cars go into the wall, but unfortunately at the higher ends of drag racing, it does happen due to engine failures like this. Just because you mentioned the cost aspect, obviously you provide a range of different blocks and they're all going to be at different price points. But if we could sort of talk about maybe some generalities of maybe percentage differences, because if we take the likes of the Honda B series that you just mentioned, or the Nissan SR20 that we've also been talking about, if someone wants to prep one of these engines for 1,000 plus horsepower, maybe 1,500 horsepower thereabouts for drag racing, or 1,000 horsepower probably a bit closer for world time attack, there's not an insignificant cost involved with sourcing and then the modifications required to make a factory block somewhat reliable at that power level. What's the sort of, could you give us kind of a rough percentage difference of how much more we're looking at to do a billet block from start to finish instead? Are we sort of talking double? Or are we talking sort of a 50% increase? What's your sort of gut feeling there, Darren?
Well, I don't know for sure how much they're spending to modify those factory blocks. And obviously, like you said, it varies depending on the block. I think with an SR20, you could probably spend $4,500 putting the steel caps in it, grouting it, closing the deck, doing sleeving it, doing all sorts of things. And at the end, you still, I mean, you got something that'll last and it will withstand more power, but for how long and how much more is a question. So if you're spending that, and then our blocks, our SR20s are retailing now at $9,900, so you're probably looking at double there. But in addition to that, in addition to the safety issue, the reliability issue, you'll make more power too. So, obviously these guys, they're spending all this money to make more power in the first place, so you've got to put some value on that.
Let's talk about that power aspect as well. So, I mean, obviously one aspect is because of the strength of the billet block and everything we've talked about so far, it allows the competitor to run more boost and make more power in that respect. I'm interested, I've had reports from other people that we've interviewed on the podcast that just simply moving from a factory block to a billet block, within reason, every other thing being equal, they've seen as much as another 100 horsepower at the same boost level, putting down to maybe the rigidity of the cylinders not flexing, etc. at that sort of boost level. Is that something that's realistic and you'd expect to see as well?
Yeah, in the 6-cylinder guys, I've had reports on 2Js at 200 horsepower more. So that's a combination of things. And so the first is ring seal. And to give you an idea, Speed Factory, when they took delivery of the first billet blocks, they were running 10.5 to 1. I think it was 10.5 to 1 static compression. And they spoke to me about it, and I it was both myself and Bill Miller advised that they should reduce that to 8 to 1, 8.5 to 1 maximum. But the engines were already assembled, and they were going to the track, and they left it. And what happened was, by the 1,000-foot mark, they had bent 2 aluminium rods on the first pass. And so what became obvious afterwards was that the ring seal in that particular engine was so much better that it actually increased the compression level, so the engine detonated at the same boost pressure that it didn't beforehand.
Right.
And then I've had other guys come back to me in like the pro classes with the 2Js, and moving from an iron block to our block, they've had to reduce their launch boost pressure from 35 psi to 26 because the engine makes so much more power that they would lose traction at 35 psi, so they'd have to reduce it to feed it in slower. So there's 2 reasons why they're making more power, and the main reason is the ring seal, and the other reason is that there's only a certain amount of energy. So what we're doing is we're converting the energy contained in the fuel into rotational energy and to move the car forward, obviously. And so, but there's only a certain amount of energy contained in that fuel. And so a large majority of it gets made into heat. But also, if you think about it, if the components are moving, it takes energy to move those components. So if the block's moving and the crankshaft's flexing and so on and so forth, what that means that some of that energy contained in the fuel is being used up to move those components or flex them rather than going into driving the car forward. So that's a small component, but it's something.
Yeah, okay, so it all adds up, particularly when some of these competitors are obviously shooting for world records. Now, coming back, something I didn't touch on when we were talking about the sleeves. With those dry sleeves, if you've got, maybe you've had a piston fail and it's damaged a sleeve or something of that nature, is it possible to remove and replace an individual sleeve?
Yes.
Okay, so that's another thing that's worth considering. There is the ability to recover from a failure like that and actually still utilize the block is quite valuable, particularly when you've got maybe close to 10,000 Australian dollars invested in the block to start with. The other thing in terms of, we talked about the Alan Johnson, Keith Black blocks earlier. It's quite common to see, if something goes pear-shaped on a pass with one of those sorts of engines and it throws a rod out through the side of the block, within reason, often that can be recovered by welding a patch back into the side of the block, putting it back in the CNC and machine it back, and basically it looks like brand new, put another sleeve in it and you're good to go again. Is that something that's possible with the Bullet blocks as well? Yeah.
So it is possible, and we have done it. So it's got limitations. It depends how badly they do it. Sometimes it just becomes more cost effective to get another block. But I would say 8 times, 9 times out of 10, they're repairable. Sometimes they don't window the block at all. They do some pretty serious damage inside, and it can be a case of there's not actually a lot of remachining to do. You might clean stuff up with a die grinder and stuff like that, but you can certainly replace the sleeves and do all that. So, yeah, we've repaired several blocks for customers for those reasons.
Okay. Let's move on to the design process. We've really talked so far primarily around the SR, and you mentioned briefly the 4G63, but obviously you've now got a wide range of these blocks that are being used in all sorts of disciplines of motorsport. Can you talk us through the design process from basically starting with a clean sheet of paper for a new engine design, how you go about basically, first of all, assessing the weaknesses that you're going to need to address, how you go about that, and then how you actually develop, prototype, and then validate that new block?
Okay, well, we have some rules of thumb in terms of addressing the weaknesses, which is, a 3/4 inch deck. We have a certain amount a minimum thickness of material around the sleeve, like where the water jacket is. So we have a thickness there that we don't want to go below. And then we have thicknesses on the outside of like the thickness of bosses around fasteners. So in the head stud area where there's a water jacket going around it, we want a certain thickness outside the thread to make sure we've got enough rigidity there. And then, of course, the main web thicknesses are just, we try and replicate what's already in the factory stuff. And usually the factory stuff is undercut and stuff like that, whereas we just leave it solid all the way through. So we try and put as much overkill in it as we can and still be able to fit the components in. So what we do is we usually want to have a bare block and then a complete engine. So if we're starting on a new project. And then what we'll do is that if it's a 6-cylinder block, we have to cut it in half so it will fit in our scanner. So we have a scanner that we use for reverse engineering cylinder head ports. So it's not actually a CMM, it's a scanner to scan surfaces, but we can use it to locate positions. So we use that to locate the positions of dowels and bell housing bolts and where the cylinders are in relation to the bell housing and so on and so forth. And we just come up with a mud map type thing that we do by hand for each side of the block. And then what we'll do is we'll come in and we use Solid Cam. So Solid Cam it's a CAM program for computer-aided manufacturing, but it has a modeler embedded in it, and that can be Inventor or it can be SolidWorks. We use SolidWorks. And so we'll come into the SolidWorks part of the software and we'll start modeling the block from scratch. So we're not scanning it like with a laser scanner and replicating the factory block. All we're doing is taking the immovable measurements that those components or those things in that component have to stay in that position and we can't move them.
So you're ensuring that it's still going to be compatible with the existing bell housing, transmission, engine mounts, front covers, cylinder head, those sorts of things.
That's right. So in most cases, you don't have to change much at all to put it in to replace the aluminium block from the cast iron block. So then we go through the process of modelling it and figuring out how we're going to do our water jacket system with the impediments that are in place because of the way the factory design is. And the thing is about that is that because I'm a machinist as well as a modeler, that can make a big difference because someone that just models who doesn't understand the machining process may model things in a certain way that you can't machine them, or it makes it difficult to machine it. And so that can add problems to it because they don't understand the tooling and the way you're going to cut things and the strategies you need to use. And so then they create something that you have to change because when you go to machine it.
So just because you can draw something in SolidWorks as a model doesn't mean that it's practical or even possible in some instances to actually machine that.
That's correct. And that's where I see one of our major advantages is that we've gone from engine builders to machinists, whereas a lot of people that have tried to do this or do similar things are machinists and they don't have the engine building experience, so they don't know how to design it in a way that'll work. So even though we're coming at it from that perspective, once we've got the model, then we'll put it into the CAM and start putting tool paths on it. And we do everything the same way. So it doesn't matter which block it is. We do it in a certain order and use tooling in a certain order, and it's like a recipe. And then you just have to change how you're going to do it because obviously the shapes are different and you might have to approach things a different way partway through the program. But even so, once you do that and then you come into machine it, what you find is you might have to come back out of the CAM, go into the modeler and change the model and then reinsert it into the CAM because there was something you didn't think of when you were modeling, and then when you come to machine it, you realise, I've got to change that. And then that happens again once you get it into the machine. So once you get it into the machine and you start actually cutting it, then you start encountering other problems where it's like, oh, that's not going to work. I'll have to go back and change it. So that process probably takes 500 hours.
Oh, okay.
And so once we've got it to that point, then it might take 4 or 5 blocks through the machine where we get to a point where we're confident we can leave it. So after that, after machining the first one and then through that next step is where I refer to it like I tune up the program. So then I'll go and look at it and say, I can cut this area faster. I can use a different strategy here. And then we might, from the first program, by the time we get round to the 5th block, we might have pulled an hour and a half out of the program because we've figured out how we can do things quicker, or the speed that we were going to do something at. We realise we can increase that by 30% because the tool can handle it.
In terms of the machining time, obviously it's going to be very dependent on whether you're dealing with a 4-cylinder or a 6-cylinder block, for example. But let's use the SR20 example. Kind of, what is the total machine time on that block from start to finish?
Probably about 15 hours.
Yeah, it's pretty substantial.
Yeah, so it just depends, like on a 2J or the Barra now, because the Barra's large, it ends up being more because the bell housing's wider, so the piece you start with is so much bigger and there's a lot more scrap. So that does vary. The SR's not too bad, it's fairly compact.
On that note, obviously, I mean, you particularly mentioned the Barra there, the wide bell housings. So you're starting with a very large piece of billet and then essentially machining away everything that isn't needed, which on face value seems like an incredibly wasteful process. Granted, I mean, it's the means to an end. The swarf or byproduct that's produced from the machining process, is that then able to be recycled and basically go into producing a new billet to start again down the track? I mean, obviously not by yourselves, but I'm assuming there is some kind of level of recycling there. This isn't just a complete waste.
When we're in full swing, we produce 1,000 kilos of swarf a week. And so we just, that gets picked up and we get paid a meagre amount compared to what we pay for the billet. We get that back, probably 10 cents on the dollar. So then that would take off, and I think they compress it into cubes and it would be exported to go to an aluminium smelter somewhere. And actually with the Barra, we've actually made the outer legs of the bell housing, we've made as a bolt-on. Because when I first did it, I thought, no, I'll just machine it. And then when the billet turned up and I saw the size of it, it's different looking at it on the computer screen. And when it turned up, I thought, oh my God, look at the size of this thing. It was 240 kilos. And I ended up having to go back in and redesign the block and just take the wings off the bell housing and make them into a bolt-on unit. And it took about 40 or 50 kilos off the billet and probably pulled 2 hours out of the program.
So that 240 kilogram billet that you started with initially, for reference, what's the finished block weigh?
Well, out of that piece, because then you've got the cradle and some other things. So out of that piece by itself, probably 40, 45 kilo. Yeah.
So essentially 200 kilograms of scrap.
Yeah. Yeah.
Okay. In terms of sort of the validation of the design in terms of whether it's going to be up for the task in terms of cylinder pressure, etc., that it's going to need to withstand, is this coming from experience and your rules of thumb, or are you incorporating any finite element stress analysis through your Solidworks software to sort of have that confidence that it is going to be strong enough for your task?
No, we're not doing any of that sort of thing. We're just it just comes from experience and then seeing what the results are from the guys in the field. But no one's actually got a block to fail as yet. Everything else around them's failed, but the block itself, we haven't had an engine failure because the block's failed as yet. So the only validation we do, that's why we ask for a complete engine when or we buy a complete engine when we're going to do the design process. So we use the block to design the block, but then we have the complete engine because we want to see how the ancillary brackets are going to bolt on and make sure that, because it could be an area where it's too bulky for the bracket to bolt on, even though the boss and the thread are in the correct position. Something next to it might stop you from bolting the alternator bracket on because it hits it or something. But then in addition to that, once we finish that first prototype, we pull it out the machine and then we build an entire stock engine and just replace the block.
Okay.
And then the engine builder here will give me a list of what's wrong with it. And then I'll go in and change the model and change the program. And then that's what we make.
So how many iterations do you sort of get through before an actual engine is run for the first time on a dyno and you get to sort of see how it actually pans out in the real world?
Sometimes the prototype, and I mentioned this on the YouTube the other day, is that Joel Granis took the prototype for the 2JZ and he used that. But that's not the same as what the second block was because we made some changes. And again, that it's nothing serious. What it is because a boss for an alternator bracket or something's in the wrong position, or an engine mount. Like on the barrel, one of the engine mount bolts was in the wrong position, and just stuff like that. So
it's not really the fundamentals of the engine, it's more the ancillary stuff of physically being able to bolt on the factory engine mounts, alternator brackets, etc., and just make the engine easy to actually install and utilize.
Yeah, I mean, it's all sorts of things can go wrong just in terms of the transfer from scanning the block. Then you've written it down on a mud map in pen, and then when you transfer it into the Solidworks software, you might have probably not put a decimal place in the wrong spot, but you might be a millimetre or two out because of something to do with the transfer. You didn't write the number down correctly or something like that. So,
human error always creeps in somewhere along the line. Okay. In terms of the actual validation on the track or whatever happens, the dyno, how often is the sort of feedback there in terms of not just the ancillary parts we've talked about, but in terms of problems that may crop up that need to be addressed in a more fundamental way, or is that pretty rare?
Catastrophic problems haven't really occurred. It's been more so that maybe they've said, we want you to put a breather here, or can you change the clearance here because the oil pump bracket we use, we have to grind the block to fit it. So like if you look at something like the RB, that's probably 5 versions now where I've just done little upgrades from what we originally had. And then something, the SR had a lot because the SR was our first. There was a lot of problems with that because, we made mistakes scanning it and different mistakes along the way. And again, that's where you learn. So now we're at the point now where, like with the Barra, the first Barra that came out the machine, when the engine builder put it together, the list was like 5 or 6 things that had to change, right? So it's just, you know what to look for in advance the more you do it.
No surprise, you've sort of learned from the experiences that you've had so far. Goes without saying, really. One of the questions we quite often get asked is around differences or complexities when it comes to actually machining and assembling a billet block versus a factory cast alloy or cast iron block. Specifically here, is there anything different that we need to be doing in terms of setting our bearing clearances? Are we going to be working off what we would do with a factory block, or are there requirements to change those clearances to suit the expansion rate of the alloy?
Yeah, so there's changes that you have to be aware of because the aluminium behaves differently to cast iron. So you're going to see expansion rates. So what we did initially was we would just put a block and a crankshaft. So we would install main bearings in a block and measure it and set the clearance. And then we would put the block and the crankshaft in the hot wash and spin it and heat it up, and then pull it out, and then measure it again. And what we saw was that the bearing clearance would open, say, 1 thou and a half. So the crank and the block would expand. It's just that the bearing housing in the block would expand by 1 thou and a half more than the crankshaft did. So your clearance is going to be higher. So what that means is when you're setting your clearances, you've got to think of it in a way that you're going to set, you're aiming for your target clearance when the block is at temperature. So if your target clearance is 3.5 thousandths on the main bearing, then that means that you want to set them at 1.5 to 2 thou cold. Then this is why you see in Formula One where they have to preheat the engine because it won't even turn over because their clearances are so tight that when it's cold, you can't even turn the engine over. Now that's not practical for what we're doing, so we don't recommend that. But that some people can do that if they in a racing application if they want to go to that trouble. But we haven't had any issues with bearing clearances, and people do get caught up on it. I've had people that have called me because a bearing clearance is 3/10,000ths of an inch different from
Right.
one before. And it's like if you speak to a bearing engineer and they tell you the clearance range on their recommendation, I mean, they might have a clearance range of 3/1000ths. So, that's where we mainly get issues with this is because people they know what they know. Like they've evolved over time. As we said earlier, they didn't go to school how to learn to do this. So they've just taught themselves over time. And maybe they've only worked on 4G63s or they've only worked on RBs and they just know what they know.
So there's a bit of unlearning that's required when it goes to actually working with a billet block.
That's right, because, once you're presented with something different, you might not necessarily intuitively know what to do. So,
Yeah. In terms of the bearing clearances you just mentioned, because there sort of are two schools of thought there, particularly if we're dealing with factory components, and we've already talked about the flex that we see under high loads. So the typical sort of approach there is to usually build the engine with slightly looser clearances than maybe the factory specification, just to give a little bit more room to move, I guess, before we run into problems with metal-to-metal contact between the bearing surface and the journal. However, if we look at a race engine, you mentioned Formula One there, and your own billet blocks, obviously we've talked about how much more rigid those components are, so we don't get that flex so much. So it's common to build the engine with tighter clearances, allowing the use of a lighter viscosity, thinner viscosity oil, and get some advantage with a reduction in frictional losses around that. So you mentioned there, yes, you can go down that route, but requires potentially preheating. So for you, the advantages of going down that route with tighter clearances, thinner oil, the juice isn't worth the squeeze?
Oh, exactly. I mean, the thing is, like those sort of issues, that's where you're talking in the normally aspirated environment. And so when we're talking in the turbocharged area, there's so much power available.
Nothing you couldn't make up with another 0.5 PSI of boost.
Well, that's right. But the other thing is, even in a drag racing environment, are you going to notice the difference in 50 horsepower when you because they don't use all the power for the whole thing anyway. But even on the street, I get guys that you say, I want to build a 2,000 horsepower street car. It's like, well, would you notice any difference if it was 1,500? No, because, it just you're never going to use that power and it's never going to get there. So when we look at things, I mean, we do things a certain way in a super stock, normally aspirated engine, where we're looking at hone finishes and bearing clearances and all these sort of things to make more power. But in a boosted application, you just make things looser because it's better to be looser than tighter. Like we say, piston clearance, people say, like the piston recommendation is whatever, 3.5, 4 thou, and then you give it 5. And they say, why didn't you give it 4? And it's like, well, you'd rather hear them than smell them. Right.
Great. It's a great saying.
So the thing is that it's not going to make any difference to the end result, but it's going to make the engine more reliable. And when you build an engine, the way you build it for a customer is different from the way you build it for yourself, because you've got to allow for someone that may do something that they shouldn't do. So you've got to leave a fudge factor in there for them.
Yeah, I 100% agree. And I think there's application does come into this a little bit. And I mean, obviously, if you're building a dedicated drag engine that's going to be 1,500, 2,000 horsepower, whatever it's going to be, then yeah, absolutely couldn't agree more. In terms of, particularly, you mentioned there about piston clearance and being able to hear them rather than smell them. Great analogy there. Where you sort of get a bit of pushback from customers, I think, is maybe more in the lower horsepower street engines, maybe 500, 600, 800 horsepower. Yeah, where it is maybe not necessarily a daily driven car, but maybe it's getting some kilometres on the weekend. It's not just used for race use, and those customers tend to push back a little bit when the thing rattles its head off while it's warming up, because of that additional piston to wall clearance until everything comes up to operating temperature. So, I mean, yeah, some application does need to be taken into account there, I think, but definitely worth considering. Now, we have talked about the use of these billet blocks in circuit race or road race applications, particularly the MCA Hammerhead. For those who maybe aren't aware of that particular vehicle, definitely look it up. It's definitely a weapon, and has been a front runner basically every year. We've been to World Time Attack in Sydney. Even there, I would say that in for most instances, you'd say that World Time Attack and Time Attack applications in general are quite unique in that these cars aren't going out and running 20 laps around a racetrack hard. They're going out doing a warm-up lap, one flying lap, and then a cool-down lap. Is there any downside, any problem, any issue with running one of these blocks in the likes of an endurance application where maybe the engine's going to go out and run for 2, 3, 6 hours or more?
No, we don't see any problem at all with it. I haven't got one running in that application. I've got them running in road race stuff where they might do 20 laps. There's some drift, which, I mean, drift is short as well, but it is fairly hard on the engines. But the way I like people or advise people to look at it, and it's not a sales pitch, but the block is stronger, it's lighter, and more durable than the factory block. So if you can use a factory block in that application, of course you could use our block in that application.
No, that makes sense. All right, Darren, I think we'll move towards wrapping this thing up. And at the end of all of our podcasts, we like to ask our guests the same set of questions. And the first of those is, what's next in the future for you and Billet Race Engineering? Have you got anything sort of exciting on the radar that you can share with us?
What's next is just continuing on with what we've been doing. We've got, as we mentioned, a new Barra, and we've moved into doing some V8. So we've got a Holden V8, and we have a Cleveland in the works. And also we're doing the cylinder head. So we have an RB30 single cam cylinder head, and we've got a 2J in America at the moment, just getting some valve train work done. And then the prototype will be back here. And then I've got a RB26 billet head in the works as well.
Safe to assume that, we already talked about when we were talking about head gasket integrity, that the factory cylinder head is the next limiting factor, and that it also moves around. So safe to assume that not only the potential to maybe improve the porting shape, but the additional strength in a billet cylinder head is going to see another boost in terms of potential performance in these high-end drag applications.
Yeah, so it's twofold. It's to increase performance, particularly on the 2J, because the 2J head leaves a lot to be desired. The RB not so much, but it will still be a better performer. But also, reliability. And also things are getting hard to get. Like everything at the moment is hard to get, but the factories just aren't supporting this older product anymore, and so people keep breaking stuff, and so we're just going to run out of it.
Yeah, I think that's easy to actually overlook, but these parts aren't getting any easier or cheaper to source. All right, given everything that you've gone through in what has been a pretty extensive career with a couple of shifts in direction so far, is there any advice that you would give to a younger version of yourself that would help fast track your sort of career and get you where you've got to faster?
I think, if anything, it would have been better to have a better idea on marketing, on how to present the business. I think we were so focused on the technical side of it that we sort of dropped the ball on that, which made, like, it extended the time in which we got to where we are. But I've talked to Marcus about this, my business partner, that like, we wouldn't be where we are today if we didn't make all the mistakes along the way, which is an obvious thing to say. But the point is that you had to make the mistakes to learn what not to do.
Yeah, and I think that's really easy to overlook is when you're just starting any enterprise, you're in that situation where you just don't know what you don't know. So there's a necessary learning curve. The other aspect that you just mentioned there, I'll just reiterate as well. And I see so many people in the automotive industry particularly, they get involved and started because they're good at a particular aspect of that, be it fabrication, tuning, engine building, whatever that may be. And that's their passion. That's what they want to do 8 hours a day, 40 hours a week. And they sort of start a business and very quickly find out that the actual work that they want to do is actually only one part of the business. And there's the accounting side of things, there's the quoting, dealing with customers, and then, as you mentioned as well, marketing, particularly these days, has become so much more critical. And if people can't find out about you and don't know what you're doing, the phone's not going to ring. So it is kind of, you got to bring all of these facets together, and it's often trickier to do than most people would think. And I think that's where a synergy can come about, where partnering with someone who is interested and passionate about the marketing of the business side of things, that works so well, and which is exactly what's happened with High Performance Academy. I mean, my side of the business is the technical aspect, and I've got my business partner Ben, and obviously now a number of staff that focus on the other aspects in terms of the marketing and the production. So we couldn't turn out what we do if it was just one person. It's just not possible. Last question for today, Darren. If people want to learn more about Bullet Race Engineering, find out more about you and see what you're up to, where are they best to go to?
Okay, well, they can find us on Facebook, and we put some stuff up there, Instagram, and then we have a new website that we did a few months ago, which has an online shop, and that has a blog on it, which we've populated with some stuff, but we're looking at putting more stuff on there, and we're actually looking at having a section there. We have a membership section, but we're looking at having like a university, what we call a Bullet Engine. I think it's Bullet Engine University or something. So I might be competing with you soon, but we're looking at trying to have a membership section where guys can pay an annual membership, and then we'll have videos and tutorials on there on hardcore engine building, where we'll talk about things that you probably wouldn't find most people would reveal in terms of how to build an engine and how to prepare it and what to look for.
Oh, exciting stuff. I'm all about education. The more, the better, and particularly, someone like yourself sharing that wealth of background knowledge from working on these engines day in and day out for so long. That's going to be exciting. I hope that helps a lot of people. We'll put some links in the show notes to those resources as well, so people can find them easier. All right, Darren, thank you very much for your time. It's been really interesting, and we appreciate you coming on to share all of that information.
Oh, thanks a lot for having me. It's been great.
All right, that concludes our interview. And before we sign off, I just wanted to mention, for anyone who's been perhaps hiding under a rock and hasn't heard of High Performance Academy before, we are an online training school and we specialize in teaching a range of performance automotive topics, everything from engine tuning and engine building through to wiring, car suspension and wheel alignment, data analysis, and race driver education. Now remember, you've got that coupon code. You can use podcast75 at the checkout to get $75 off the purchase of your first course. You'll find our full course list at hpacademy.com/courses. Important to mention that when you purchase a course from us, that course is yours for life as well. It never expires. You can rewatch the course as many times as you like, whenever you like. The purchase of a course will also give you 3 months of access to our gold membership. That gives you access to our private members only forum, which is the perfect place to get answers to your specific questions. You'll also get access to our regular weekly members webinars, which is where we touch on a particular topic in the performance automotive realm. We dive into that topic for about an hour. If you can watch live, you can ask questions and get answers in real time. If the time zones don't work for you, that's fine too. You're going to get access as a gold member to our previous webinar archive. We've got close to 300 hours of existing content in that archive. It is an absolute goldmine. So remember that coupon code podcast75. Check out our course list at hpacademy.com/courses.